All right, continuing with inserts, here are some other types. The unthreaded external diameter. Now, a lot of these you'll buy something made out of plastic that has either this type or this type in it, where you drill a hole and then ultrasonically force the insert in, or you mold it in place. And then if you go to hang a picture or put up a shelf or something, you use these type in drywall. The little old plastic expandable type, which will hold a little bit, but not a lot. So that's the more of the industrial type inserts. Now here's another one that's made by a company called PEM, and it is a kind of a combination between an insert and a nut. It locks in place on the back side of the sheet and bites into the edges of the hole. Now, these are usually used for the thin sheet where there isn't enough depth to put in an insert, but they're not usually used for structural applications, critical things, due to their unpredictable clinching capabilities, because you don't know how it's going to clinch into the surface, how much damage you'll do, and stuff like that. Now, nut plates. Nut plates are sometimes called anchor nuts also. They're used actually as a blind nut. Blind nut is, of course, is used in an inaccessible area. That's why it's called blind. You can't get to it. They can be fixed or floating, and they can have most of the locking and sealing features of a regular nut. But a floating nut plate does not provide angular misalignment of fasteners. We had a case here one time that some people made that mistake. Floating nut plates only float parallel to the surface that they're mounted on, so that you can't tilt them sideways to make up for misalignment. Now, they're also used on a sheet that's too thin to tap. So the aerospace companies use them more than anybody else, because you have to drill 3 holes to install one. So that's a lot of labor. And they're normally, here are some samples of the fixed type, which is just a solid one. And you drill the 3 holes, one for the bolt to go through into the threaded part of it, of the nut plate. Then you have 2 rivet holes for installing it so that it won't rotate and stays in place from now on while you thread into it. Now that's the 2-lug type here. Here's what we always call the Mickey Mouse or corner plate. You can use those in tight corners. Here's the 1-lug type. The 2 rivets are back here. And here's the seal type, where you want to seal the thing, say if it's going to be on an airplane in a place where water would come in when you were moisture or something and you wanted to seal it all together. You can get them that have the sealing capability. Now the floating type is really, the plate has slots in it, if you will, or bent up tabs here, so that the threaded portion of it can slide back and forth. But you see, as I mentioned before, it can only oscillate back and forth this way inside, so it won't tilt to take up any angular misalignment. The Mickey Mouse is the same way, and the 1-lug and the sealed and the here's one that has a replaceable nut, and this is used some due to the fact that if you screw up the threads on one, then without drilling out the rivets and replacing the nut plate, you can take this thing out and slip another one back in place. So those are kind of popular in some installations. Now going into the subject of threads, and that is a big subject. The geometric information on threads, you can find more specs than you know what to do with in ANSI, NIST, Federal Standard Handbook H28, and so on. So I could have put 100 pages of thread tables in here, so I didn't bother to put any of those in. So you get into what is common, and the most common inch threads are the UNC and UNF, Unified National Coarse and Unified National Fine. And then some of the others used are the UNEF, Extra Fine, UNJC, JF, and the UNR and UNK. And those are maybe not, the last two are not familiar with you, but they are still used and in existence. And then you can have cut or ground threads where you're making a one-of-a-kind type situation. Now, metric fasteners are available in coarse, fine, and J threads. They're covered by ANSI and H28 specifications, but the aerospace ones, as I mentioned earlier, are covered by the NA and MA specs to cover the materials and geometry, plating, and everything like that to make sure that you get what you want when you order them. Now, as far as thread definitions go, we talk about pitch diameter, which is the center-to-center distance between, or pitch, I'm sorry, is the distance between threads. And, of course, for the English inch system, we call it threads per inch. In the metric system, it is the actual distance between threads. And we have major diameter, which is the largest diameter of the threads, and the minor diameter, which is root diameter, and a vanish cone, and so on. And I will have, shortly here, we'll have a table that I can point all these out. Here is the crest is the top of the thread, flank is the flat portion, pitch diameter is the theoretical diameter where the shear thickness of mating threads is equal. And now if we go on to the table, maybe I can point these out. The pitch distance between threads is here. And here's one that I want to point out while I'm here because Betsy had so much trouble getting the scanner to get this one in. This is the thread lead angle here, beta. Here is the vanish cone area here where you have incomplete threads. And the pitch diameter is this heavy line here, right there. And then you have the OD here, and then the flank of the thread is here, and the crest is the top of it. And there's all sorts of things on there that you probably don't even care to know about. One of the things that's a little confusing on this that I want to point out is that right here is the end of the threaded fastener that is going into the internal thread, this part being internally threaded, just in case it doesn't show up on your copy. Now, on the thread pitch and lead, of course, I mentioned about the, in the inch system, is threads per inch, like a quarter 20 is a quarter-inch diameter with 20 threads per inch. And in the metric system, you might have a, say, an M8 by 1 or something like that, means there's 1 millimeter distance between threads. And then here's something, the lead of a screw thread is the distance that the nut will move forward on the screw per one 360-degree rotation. And we hassled this one a lot when we did our drafting area manual. And for a single lead thread, which most of us are familiar with fasteners, the pitch and lead are the same. But now when you want to go to a double lead, it'll move forward 2 threads per 360-degree turns. And so the best way to visualize this is the thread on a milk jug or a bleach bottle or something like that, where 1 revolution puts the lid all the way on. That's probably triple lead because the thread has more angle to it. Now for rolled external threads, the R in the UNRC or UNRF indicates rolled threads, and actually this terminology is not used that much because up to about 3/4 inch diameter threads are rolled, cold rolled by the fastener manufacturers. And then when you get to larger diameters, you got to have some preheating in order to roll threads. And you also have to, as I mentioned earlier, way back, you have to make sure that your bolt stock is annealed prior to starting, to have it as soft as possible, because you get cold work on the material during forming, and of course the harder it gets, the harder it is to form, so you want to start out with it as soft as possible. And here's an important point to remember. The heat treating of commercial fasteners is usually done after all the forming operations are completed. But then when you get into the high strength stuff, it is heat treated before the threads are put on. They're cold rolled in order to increase the fatigue resistance and actually make the thread stronger, because you put residual stresses in the thread surfaces during the cold rolling. Now on UNC threads, of course, that's the most common general purpose type thread. They're a little deeper than fine threads because you have since the coarser threads and the 60-degree angle between threads is the same, so you go a little bit deeper, so the minor diameter is a little bit smaller, but makes them a little bit easier to assemble without cross-threading. And of course, just about all small fasteners are coarse thread, because it's kind of hard to make 80 threads per inch or something like that on a fastener. So anything usually up through a number 8, which is a 1/64 diameter, is coarse thread, even in aerospace. Then the UNC threads, the easier to remove when they're corroded without stripping the threads. There's different schools of thought on that as to how much easier it is, if any, and so on. And they're sloppier fit usually, although you can get them in the tighter fits, and I'll be covering the classes of fit later on. Now on the fine threads, UNF, that's kind of the standard in the aerospace industry. And nearly all fasteners with strengths above 150 KSI are UNRF or JF. They have a slightly larger minor diameter than the coarse thread. It gives you a little bit larger net cross-sectional area. And the smaller lead angle, since you have more threads per inch, so you have a flatter angle, so it makes it a little bit easier to adjust them. The extra fine threads are used for tapped holes in thin or hard materials and holes with short edge distance. They're also used on where you have adjusting screws. Vernier screws for adjusting things are usually extra fine threads, but they're not used a lot in the ordinary structural fasteners. The UNR and UNK thread comparison, now this is kind of a little bit of an oddball thing. UNR threads are the same as UN threads most of the time, because they're all rolled, except that the root radius must be rounded. But however, people can say they've rounded the root radius, but they didn't, because there's no requirement for measuring it. So if somebody says, yep, I rounded the radius on these fasteners, they may or may not have. And there is no internal UNR thread. Now UNK threads, which is, I'll have to admit, it's kind of an oddball one, are the same as UNR threads, except that the root radius is measured and toleranced, but we haven't bought any of them around here, I don't think, lately. Have we, Ron? Okay. I didn't remember buying them. Now, constant pitch threads are used a lot in larger diameters and used to tailor a design to a particular need. For example, when you get up into fasteners larger than an inch diameter, they usually will go to constant pitch because the regular threads are hard to form. They get too big. In fact, in case you ever get anything formed, any of you designers, the limit, I understand it, is 4 threads per inch is as big a thread as you can get anywhere. And I've never seen one called out. I've seen them down to 6, I believe, threads per inch. So usually what you do is go to constant pitches of 8, 12, or 16 threads per inch. That way you can roll the threads, even at elevated temperatures. And it makes it a lot easier to adjust the torque tension because you don't have to turn as hard to get the thing to move. For instance, wheel pullers, bearing pullers, normally have real fine threads on them to give you that adjustment so that you can turn them without using a 3-foot braking bar. Left-hand threads, they do exist. In fact, Chrysler used to put them on their cars for some reason or other, and people were always turning the wrench the wrong way because they try to tighten them, be tightening the threads instead of loosening them when they got a flat, because they didn't see that somewhere on the lug it had an L stamped on it, meaning it was left hand. So there's not very many of them used. Gas grills are one of the places, the gas grill tanks, they use them. And on turnbuckles, rod ends, and where you have left-hand nuts, usually they put some sort of a marking on them. If they're not big enough to stamp LH on them, they will put notches on them or something to flag them to indicate that you do have left hand. So just to make you aware of the fact that left-handed stuff does exist. Now, J threads. The J thread is made in both external and internal forms, although the internal form is a little bit dubious. And they have a much larger root radius than the UNF or UNC threads, and inspection of this radius is mandatory if you catch them. Since the root radius is larger, the minimum diameter is larger, giving a higher net cross-sectional area. And it also reduces the stress concentration factor in the threaded area. So normally threads above 180 KSI will be J threads. And some nuts have J threads that are rolled on them, but there are no J taps for internal holes. Now the UNJC threads are coarse threads with the same characteristics as the UNJFs. However, they're not that common, except in the small sizes up through a number 8. Now a J bolt requires a J nut, but a J nut will fit a regular bolt of the same size thread because the radius is not that critically controlled on the nut, even though they say it is. And if you can go into the ANSI B1.1 specs and all that, get all the information on the thread geometry, everything more than you care to know. Now, a tapped hole has cut threads because that's the only way you can get it formed is to cut it. So regardless of the type of thread and form that you're talking about. Internal threads. Internal threads are cut with some sort of a tap. Although you can roll some on the nuts, they do have capabilities for rolling them. But the tapped holes are harder to inspect than an external thread, so their design margin should be higher to allow for that. Because really, if you want to check an internal thread and you want to measure the root radius or something like that, about the only way to do it is use, there's a dental plaster that you can put in there that is soft enough. Like for instance, if you get you probably got impression at some time for a bridge or something like that for your mouth, they use a soft type of plaster that will maintain the configuration, but you can strip it out. Well, they use stuff like that to check internal threads where they need to check them. So, but that's a lot of trouble to mix the stuff up, get yourself a cast of it, and then use an optical comparator to measure it. So it's usually not done. And there is no J thread for tapped holes, as I mentioned there earlier. Now, thread classes or fits. This is the number associated with these is associated with a tolerance band. So the class 1 type thread would be the nut and bolt you buy from the hardware store, and you put the nut on the bolt and you can jiggle it back and forth because it's so sloppy a fit. That would be a class 1. Class 2 is the industrial grade. Class 3 is the aerospace grade, where the thing fits quite snug. And the aerospace industry uses primarily the class 3 threads. Now, you can go into H28, Federal Standard H28, or the SAE Handbook, or ANSI specs, and so on, and you can find out what the tolerance levels are for each one of these threads for a given class, if you're so inclined. Cut or ground threads. They're normally made on a one-of-a-kind fastener for a specific application. So, but remember that tapped holes are cut so that you can't cold form threads very well in a tapped hole. So cut threads are weaker than rolled threads, and thread cutting destroys the grain flow in the piece of material. Now, this is one of the reasons why your super strength bolts have forged heads, because you have to maintain the proper grain flow in the head to shank area in order to cut down on stress concentration. Now, for metric threads, once again, to refresh your memory on them, they're usually described as a M, and then the diameter like an M8 times the pitch, whatever it is. And the example I've given there is that one, I believe, that's fine thread for an 8 millimeter diameter. And the pitch value tells whether the thread is coarse or fine, but there's no designation like an MC or an MF to indicate whether it's fine or coarse. So if you're unfamiliar with metric threads, about the only way to tell is go look it up in a table to see whether you have fine or coarse threads. The only further identifier on the metric is a J, where you have J threads. So, and remember also that the property class of the material has to be specified to tie down the strength requirements. So just don't call out an M8 by 1 and say that's the end of it. You've got to also give a property class to tie down the strength. Now, metric thread classes, they have 2 diameter tolerances, which is kind of seemed odd to me, but nevertheless, that's the way they do it. First one is for pitch diameter, and the second one is for crest diameter, which is the major diameter for external thread and the minor diameter for internal threads. Now, if you only give one value, they're applying the same tolerances to both crest and pitch. If they give 2 values, you have then two different tolerance levels for the 2 of them. Now, their numbers go from 3 to 9 on the tolerance levels, with 4 to 6 being the normal range for the tolerances. And they give letter number values for the pitch and crest diameters where they have different tolerances. Now, I think this is the next, no, I'm sorry, it'll be the one after this. On the, you have sample callouts given in the ANSI Y14.6. And on our next table, which you can go ahead and go to, Alice, we have the we have some sample callouts here. This would be a way of calling these out, and you can read them in your handout. I'm not sure whether you can read them anywhere else. But now, notice on the pitch diameter here, you have a 4H, and on the major diameter, you have a 6H. So you have two different levels of tolerance on them. Now, if you come down to the other one down here in the below, where you have the internal thread, you have a 4H and 5H for your pitch and diameter tolerance. So with the metric, it is you have to really pay attention to what you're calling out, because to me it's more confusing. And then of course on that slide there was also a single number given there of 6, I believe somewhere along the line. No, it's the next one that has a 6 on it, where you have the same tolerances on both the pitch and minor diameter. So this next one, it gives you also a way of calling it out, and an explanation here on the left on the external, internal, and so on. And one of the things they have added there, which we will be covering later on, are the methods of inspection. The system 21 and 22 and 23 gauging systems. When we go into inspection and acceptance of fasteners, we'll cover those. Moving on, here is a comparison, and to me this is a nice thing to have, because it kind of gives you a yardstick to measure from. On the comparison of inch to metric on the thread tolerances. Now, somebody asked me the other day about what would be a class 1 in metric. See, I don't have a 1 on there, I just have the 2, 2, and 3. And I think it's an E classification in the tolerances, because metric usually does not come with that classification. It's normally either the 6 is usually about what they call out for it. And so I think it's an E. But anyway, if you go into the ANSI specs, they give the tolerance bands in there. And I think that that is the one. If you, IFI puts out a manual or a book on metric fasteners that has all of the different ANSI stuff in there. So anyway, that is something you can refer back to. Now here's for thread relief. I put this in here because it's something that is quite common to have a thread relief, particularly on what the shoulder bolt that we'll be covering next. But this diameter on the thread relief should not be larger than the minor diameter of the threads, or you get in trouble when you try to thread it. And the sometimes in a tapped hole, you even put in internal thread relief, where you don't want to kind of run your tap in there and have incomplete threads and all sorts of notches and gouges and everything like that. So you have thread relief where you, when you tap through, at least it will come out clean. Since thread relief was a part of a shoulder bolt designation, I went ahead and put in a shoulder bolt here. Now, they can be used as an actuator pin when you're tightening the shoulder up against the surface to tighten it up, and then using this big shank for an actuator pin. They're used some in disc brakes installations on cars. On some of them you use a shoulder bolt to tighten them down because you want to have a loose fit on the shank and a tight fit, so they Loctite them in with this threaded area here. The only thing is a shoulder bolt is real bad if you put it in single shear, because this reduced cross section here has a high stress concentration on it if you go into bending. So it will bend very easily there, so you got to be careful to make sure the top part of it near the head is supported when you're using it. Now for tap threads, I don't know, probably a lot of you shade tree mechanics have done thread tapping, and you got to do it carefully to get the proper thread with the correct alignment. And this means they usually tell you, if you're doing it yourself, what size drill to use, drill the hole with. And then the problem is to start that tap by hand and get it to go in properly so you don't wind up with something lopsided. Well, of course, on machines you can get away from that. But sometimes on critical applications they actually have to drill a hole and then ream it to get it to exactly the right diameter for tapping. And of course the required length of a tapped hole is dependent on the hardness of the material and the tensile load developed by the installed fastener. And one of the key things here that you got to think of too is the length should be based on complete threads, because when you start out you don't have complete threads and you don't wind up with complete threads at the bottom. So we have an example here of the different types of taps. Here you start out by drilling a hole with the tap drill. Then you use a tapered tap, which has a whole bunch of incomplete threads on it. In fact, 7 to 10 of them are incomplete. This gives you something that you can start better. Then you have a plug tap here, which has an intermediate one that has fewer incomplete threads. And then if you have to make the hole tapped all the way down, then you use a bottom tap or a flat bottom tap here to tap it down to where you only have about one incomplete thread. Now my brother is a retired millwright, and he said that when they got them at the steel mill, they usually got them in sets of 3 like that, so that you could start out with your tapered one to start the hole and then go to the other 2 to finish it up, so that you'd wind up with a decent tapped hole. So we will pause here and resume on threads after the break.